Thank you, Jack, for that introduction. So I actually changed my title a bit to Formation and Destruction of Resonant-chain planetary system. So a key prediction of modern planet formation theory is that planets migrate as they form in a protoplanetary disk. This is due to gravitational interaction between the planets and the disk itself. And if you sum the Lindblad resonance and the co-rotation torque, the net effect is usually for the planet to migrate to a central star. Now imagine you're forming several planets together and they're all migrating together. Then the period ratio between neighboring planets can change continuously. This is because heavier planets usually tend to migrate faster. So once the period ratio hits one of the resonance, say 3:2, here the gravitational perturbation between different planets can end up coherently. And eventually, a potential well is set up that can lock a pair of planets into resonance. And once locked into resonance, the pair of planets can migrate together, maintaining that period ratio. So the end product is usually a whole series of resonance. For example, shown here, we have 4-3 and the series of 3-2. So this is known as the resonant chains. So that's what the theorists tell us. On the other hand, if you ask the observer, they'll tell you that resonance appears to be quite rare. So on the left is observed period ratio between neighboring planets in the Kepler sample. And I've labeled the low-order resonances using vertical dotted lines. So most of these planets are non-resonant, as indicated by the broad distribution of period ratio. If resonance would dominate, you will see a series of delta functions near the various resonances. One thing to note is that most of these confirmed planetary systems are quite mature. On the right is the age distribution, spanning somewhere between 1 gig a year all the way to more than 10 gig a year. And the median age is 4.6 gig a year, quite similar to the solar system. Okay, so the king of you may notice there's some peaks near some of the resonances. For example, 3-2 and 2-1 are the most prominent. But if you focus on the near resonant peaks and further zooming on them, these near resonant systems still show about 1 to 2% deviation from a perfect integer ratio. Here, the number delta is simply defined as the observed period ratio divided by the nearest integer ratio, and you normalize against unity. So previous work have claimed that about 15% of this mature sample are currently near resonance. Okay, so the theorists consider resonance capture to be quite effective and efficient. So much so, one would expect the vast majority of young planetary systems should be near resonance. However, as we have seen for the mature system, only 10 to 15% are currently near resonance. So what is going on? So one idea that was put forth by Andre, Sean, Ruching, and others is the break the chains model. The idea is that over hundreds of million year or giga-year timescale, dynamical instability or other evolution process can slowly make the system lose their initial resonance. So the smoking gun of the break the chain model will be a sample of young system that still show resonance before dynamical evolution has had the time to disrupt them. So thanks to the TESS mission, which surveyed more or less the entire night sky, we now have a decent sample of young planetary systems shown on the left. So last year, my group showed that for young system, younger than 100 million years, there's so far about 8 systems so far. And what's plotted here is the system age on the y-axis and the orbital period on the x-axis. So each system is a horizontal line. So I've also labeled the pair of planets that are near resonance by the period ratio, as well as the deviation from that integer ratio. And non-resonant planets are not labeled. And at a quick glance, you can see for the young sample here, all but one system shows some sort of resonance, which indicate that resonance is very common among the young sample, almost 80 to 90%. If you move on to adolescent system, between 0.1 to 1 gig a year, there's slightly more system here, 16 of them, but only a subset shows resonance at about 30 to 40% level. For the mature system, there are more than 1,000 of them, so I couldn't show them on a similar diagram. So what's shown here is a function of age, the resonance fraction. As you can see, if we count systems in resonance or pairs in resonance, both of them show this consistent trend that for the young system, younger than 100 milliyear, resonant fraction is rather high, 80% or so. But by the time of a few hundred milliyear, they dropped to 40%. And as the system matured to several gigayear, it further drops to about 15, 20%. And on the right is, again, the pure ratio distribution. As we have seen for the mature system, it's furnished a really broad distribution. But for the young system, you can see it's indeed a series of delta functions near the resonances. Okay, so if young planets are near resonance, what is the dynamical implication? On the one hand, we have seen cases where the resonant chain survived for many gigayears timescale. The classic example is Io, Europa, and Ganymede's resonance around Jupiter. As far as we know, it probably survived for the entire age of the solar system. We also have the 7-planet resonant chain around TRAPPIST-1, whose estimated age is more than 10 gigayears old. So is it the case that resonance promotes orbital stability? Or is it the case that, the finely tuned resonant architecture is actually metastable as proposed in Andre's paper? So the short answer is you have to put the planet in the true island stability, or so-called in resonance, to make the resonance protective. If you just haphazardly put the planet near resonance, the result is usually detrimental to the overall stability. And the classic example is the Kirkwood gap in the asteroid belt. In some of the resonances, you see deficits of the asteroid, notably 2-to-1, 3-to-2 resonance. But what's less talked about is the other overconcentration of asteroids near some other resonance, most notably the Hilda group at 3-to-2 resonance. So the difference between this group is the difference between libration and circulation. This is a related problem of a simple pendulum. In the libration case, this is a solution we are familiar with. The mass just oscillates around a local equilibrium point with limited amplitude. In the circulation case, the energy is so high that the pendulum can go all the way around and explore all the parameter space available to it. So in our solar system, we have definitely seen cases of librating resonance. And a classic example is between Pluto and Neptune. Even though Pluto's orbit is so eccentric that it eventually crossed Neptune's orbit, but the libration ensures whenever Pluto has crossed Neptune's orbit, but it doesn't do so with a close encounter. From the perspective of Neptune, Pluto is always far away. If the situation were in a state of circulation, then Pluto may explore a larger part of the parameter space, and you may eventually have a close encounter. And a similar situation applies for the Hilda group. Whenever the Hilda group comes close to Jupiter, it actually do so at one of the Lagrangian points. So the perturbation there is rare, is weaker. Okay, so 2 years ago, my group published a poster child of resonant-chain system named QI1136. There are 6 planets here with periods between 4 days and 40 days around the Sun-like star. And we measured the system to be about 700 million years, so it's one of the adolescent system. And the key point I want to make is that earlier we talked about near resonance system having this 1 to 2% deviation from resonance. But this system, surprisingly, has very small resonance deviation at about 10 to the minus 4 level, much smaller compared to the other near resonance system at mature age. And by modeling the transit timing variations in this system, which contains interesting dynamical information on the system, we found that the various planets are indeed in a state of libration. And if we do an N-body simulation using the posterior from TTV, we can see that the various resonant angles are indeed in a state of libration here. And one thing we also found in the simulation is that the innermost planet is on a 4-day orbit, and this is more or less exactly where you expect the disk to be truncated. Okay, so moving on to even younger system, I suggest you to check out the poster by Mutian, in which we analyzed the 200 million year QI2676 system. And quite surprisingly, several of the younger system, 20 million year old AUMIC, 20 million year old V1298, and there's 200 million year old QI2076, they all seems to be in a state of circulation already, even though they're younger. And if we integrate the system over in time, we found that the stability timescale is indeed of the order 10 to 100 million years if the eccentricity of the system are large enough. So if some of these young systems are near resonance instead of in resonance, what could have happened? So there are two theories that are increasingly seeming more promising. One idea is that the disk itself may be turbulent, so you don't have smooth migration. Some stochastic forcing during this migration can deposit the planet wider or nearer to resonance. Another idea that was put forth recently is that the inner disk is actually complicated, and the inner disk actually recedes as the disk disperses. And at the inner disk, you may have diverging force on pairs of planets, and that may eventually put them slightly wider of resonance. Okay, that's all, and I will leave up my takeaway slide points here. Thank you.
Thank you, Fei. Time for questions. Ichiro.
Yeah, Ichiro Kokubo from National Astronomical Observatory, Japan. That's very interesting results. Did you also check how the orbital separation between, adjacent planets measured by Hill radius also depend on the age of the system?
That part we haven't checked, but be glad to check together on that. Sounds good.
Thank you.
Ralph?
Ralph Pudritz, McMaster, and that very interesting last point that you made about turbulence possibly moving things away from resonance. Is the amplitude of the turbulence sufficient in the inner disk to do that?
So we haven't.
You need the MRI or?
Yeah, so we haven't run a simulation including n-body and the turbulent effect. If anything, that kind of prescription will be simplified. It will be pretty simplistic, right? Because ideally, you want to couple a hydro simulation with in-body. Maybe Zhaohuan's group is doing that. But what we're doing here is purely in-body with a very simple prescription of how migration works. It's usually a power law. Yeah.
Thanks.
Matt Hoy?
Hi. Interesting about the younger systems. I'm just curious, is it just number statistics that you're only finding the ones that are near resonant and you're not finding the resonant systems?
Yes. So one possibility is that here we are focusing exclusively on multi-planet systems. So there are a bunch of other young planetary systems which only throw a single planet. For example, this one here, this is a single planet system, but it does show TDVs, and from detailed TDV modeling, it is revealed there's another resonant planet. So to rule out that question, we should analyze all of the young systems, including the signal system, for TDV analysis, and tell, well, definitively if the single system are also near resonance.
Yeah. And in Kepler, incidentally, there are a lot of singles that have TTVs, although the fraction of singles with TTVs is smaller than the fraction of multis by a considerable amount. Richard?
Richard Nelson, Queen Mary University of London. Thanks for a very nice talk. Very interesting work as well. I wonder, it's difficult and you're dealing with small number statistics, but if you divide the systems to, say, low mass planets versus higher mass planets, do you see any systematic changes when you do that sort of slicing of the data?
If you look at the planet size here, some of these young planets seems to have Jupiter size.
That's what I'm looking at.
But TDV mass measurement revealed that they are actually between 5 and 15 years mass. All the radius, the radius so high is purely due to radius inflation at a young age.
Okay.
None of these planets here are giant planets.
None of them are. Yeah. Okay. Thank you for that clarification.
Okay, Andres.
Andres Dor, Rice University. Fantastic talk. So I just have a tiny comment about this, the effects of turbulence for the formation of the Resonant-chains. Back in 2017, we did some simulation and we didn't find any large difference between the final states of the system for a viscosity of 10 to minus 3. Okay. So when the planets migrate inwards, the effect of turbulence becomes weaker because the length of the density perturbation becomes too small to move planets around. Yeah.
I see.
Okay. And go ahead. We got two more questions on this side. And Stephen, could you come up and start setting up, please?
Bennett Skinner, McMaster University. You're definitely getting killed by small number statistics on this question, but have you looked at all at, with age, the precise types of resonance you see, first versus second order resonances?
Yes, so that's ongoing work. There's limited data for some of these young systems. So I mentioned detailed characterization for 2 systems, and I know another work has just been submitted, but that's even smaller number of statistics, maybe 3 or 4 systems where we know the dynamical state.
Thank you.
Yeah.
Hi.
Last question.
Yes. Emerson Tao, UC Santa Cruz. I noticed in the plot that was just up, the adolescent systems as we were, with the young systems, it was both like relatively small, rockier planets and the larger planets. They all had resonances, but as they aged, it looked like a lot of the smaller planets maintained resonance, while like larger planets didn't. Do you think there's a specific reason for that?
Yes. So if it's a picture painted by Andre and others, you expect giant impact collision, and it may be the case that during collision you have merger, and the resultant planet may be larger. I guess that would be an interesting follow-up study using this sample.
Thank you.
Let's thank Fei again.